I'll be presenting today low resource and actually trustworthy AI in healthcare. So most of my research is around healthcare. So I will be focusing or showing examples around that today. So we will first get into low resource settings. What does it mean? And we'll see the examples of low resource settings in healthcare. Then we'll talk about AI and healthcare in such low resource settings. Then we will briefly touch upon trustworthy AI. So when we say low resource settings, what does it mean for you guys? Low resource. You can think of low resource in many ways. And one example is lack of experts. We've got, let's say you have health posts, hospitals, clinics, different areas. We need different healthcare professionals there to function and deliver quality services, and there could be lack of that. Typical examples are health centers in rural areas, or even sometimes in district radiologists is scarce even in towns, many towns of many countries like Nepal. It could be lack of devices, algorithms, or technologies. These days, in healthcare, in medicine, technology is very important, and there are many different technologies. For example, imaging devices. They can be unavailable or they can be extremely expensive. Now, in the context of AI, as more and more AI services come into healthcare, the lack of those services, computing powers, or in different settings such as the internet. So these can also, there are different environment settings which can make it low resource. A typical example, this is not just in Nepal, but in many countries where you have public health settings where, if you think of big hospitals in big towns on the top, there are very few of them in a country. And as you go down towards municipalities, wards, you'll have many health posts. And people accessibility, in terms of people being able to quickly go to a health post, it's large number of people can go in posts or institutions that are on the bottom of this figure. As you go further up on the top, it's harder, access is hard. You all know in big hospitals it's not easy. You have to be in big queues if it is a government hospital. If it is a private hospital, it's expensive. So it also is an issue of accessibility from financial context. Any other kind of resource? These are typically easy to see, and people talk about these two kinds of resource, healthcare, in healthcare settings, the lack of resource. Anything else you can think of in terms of resource constraints? Maybe not much talked about, it is talked about, but when I talk with people, sometimes they think less about this, but this is also an important low resource, I think, is the lack of research and innovation in specific topics, such as neglected disease. There are many diseases which have been there for decades and been affecting large majority of world population. But if you look into the amount of research that is being done on those topics, such as tuberculosis, cervical cancer, malaria, dengue, a way less amount of funding and way less number of scientists work on those topics compared to other topics which affects richer people. So that's also low resource in terms of which diseases are being researched. The other low resource is, for example, ChatGPT or all these large language models that are coming. It's fairly powerful. You can do a lot of things with that, but people who can speak English are most benefited with those technologies at this point of time. People in many low resource languages, they cannot use this. If you want to build a very good healthcare bots for people speaking local languages, many in Nepal and in many in South Asia or Africa, those languages, these bots don't aren't useful yet. And when there's less research, less investment, and there are many different kinds of resource constraints. This is also resource constraint settings. So today's lecture will go around examples and research directions we are taking. Most of the examples will be from the research we are doing in our group here. And we will see why and where what we are trying to tackle in this resource settings context. Broadly, within NAMI, there are multiple research groups. The group that I work in, I lead, is the Transforming Global Health with AI at TOGAI, and we work on visual data, imaging data, lots of imaging data. There are multiple projects around that. We work with languages. We have various projects on that. And we work with other non-imaging or non-language data, such as genomics or signals in various topics. So this is just a broad overview, but we will not go through all of this. Rather, we will try to see low resource settings. But just before that, in terms of the theme, you can look at the same thing in a different perspective also. So what we are trying to do with TOGAI in general, or what kind of problems we want to solve, is first, the way these computing and the sensors are being available in these days and AI coming into the picture, there is a big possibility and big opportunity that we could empower general public for prevention and early detection. There are a couple of projects we're doing on this, such as low-cost paper device with smartphones to estimate pesticides in vegetables or fruits. I'll not go into the details today, but if you look into the website and our publications, you will see, because pesticides, when you eat in vegetables, this kind of pesticides are in some sense toxic substances. It can cause harm, but you prevent. So if you want to prevent that, you should be able to control that. Or wearable sensors could be useful to detect earlier, identify potential issues that might come in future, and then do more preventative medicine. So this is a new emerging field. That's one theme we're trying to explore, which we will not talk much today in the context of low resource. The second one, broadening what I call as broadening the scope of health services in primary and community. We will see a few examples of this today, and I really believe this is one of the major themes that can fundamentally transform the way health is delivered around the world, where you have primary health services, community health services, all these rural areas with health posts. The idea is to use the same manpower, same people, same context, almost with the same devices, but what you add is now AI-powered services. So you give AI, assist with AI those people with those devices, and you can tackle many, many different diseases at the early stage. And this is where I think the healthcare will go, or should go, in the next decade if we really want to make any big impact in terms of improving quality of health services. So that I will give a few examples of that. Sometimes we need new technologies, new devices to assess, to understand, or to see human body and the potential diseases in new ways that was not possible before. We will see a couple of examples on that direction. The last theme we are exploring is also population-based studies. What does it mean? For example, you have a drug that you are taking here, or doctor diagnoses certain abnormality based on certain structure or certain morphological shape of certain anatomy, let's say. But is that abnormal, normal on which population? Because depending on ethnicity, depending on demographic, depending on age, in healthcare, what kind of drug, what dose, a lot of things can depend on these different factors. But most of the time, you will see many drugs are being researched, and the dose or the abnormality or normality is being defined on Western population, and then it's just extrapolated here, and it's not optimal. So this is another where we understanding better the population, local population, is important, and especially with imaging data and quantitative imaging, there can be many research we could do in this. For example, what's the average hippocampus? Hippocampus is a memory in brain area that stores memory. What's the size, volume in Nepali population? And then it can shrink as you age. But if you have diseases like Alzheimer's, it accelerates. So if we want to detect early those in those populations, what is the normal and abnormal? This needs to be population specific. And if you want to do that, you could have brain MRIs of hundreds of thousands of people and then calculate volume quickly with AI, and that can help, which previously one would have to manually estimate the volume, and it's very hard to do large-scale studies with that. And you can think of heart, cardiac disease and heart morphology if you want to explore if there is some certain correlation on those. So there's a lot of things you can do with that, which we will not go today. But in the end, it's about bringing access to information, quality health services, and health care. Basic health care is the right of everyone, I think. And so in a bigger picture, it's what we want to do. Now let's get back to today's topic, which is low resource settings in healthcare and AI. So let's see some examples of how we can address or try to tackle lack of experts, especially when you want to scale certain kind of diseases. And this is with what I call as AI-powered task shifting. So if you look at task shifting, the term itself, it was widely used, or it's still used widely in public health. And what it means, let's say, it means a task which is usually done by an expert, let's say a radiologist or a consultant. So if the radiologist is not available in a community setting, then can we shift that task or allocate that task to someone else who is not as expert as radiologist, but still can do some part of those tasks? So that is task shifting, and it's commonly done in public health. For example, nurses do certain things, or field medical officers do certain things that usually an expert, a consultant does in a big hospitals. So that's task shifting. But the challenge with task shifting is you need to train people regularly, you need to monitor them regularly, and then if it's the same nurse, let's say, and you are adding tasks, you ask the nurse to do the task of cardiologist, you ask the nurse to do the task of radiologist, you ask the task to do the same nurse to do the task of gynecologist, it doesn't scale. It doesn't scale, right? But this is where I think AI-powered task shifting can play a major role, because you could have AI models for tasks that is usually cardiologist does, AI model that a gynecologist does. So when you have multiple these with AI and it assists the same nurse, then the same nurse could be able to do much more, because the nurse, they have to do less on their own. And same with the training. If you want to train, if you can build personalized training systems for these task shifting non-experts at scale with AI, with real examples, you can do a lot. So with this context, let's see at one work that we are doing is AI-assisted visual inspection for cervical cancer screening. Cervical cancer, if you identify a precancerous stage, there is a certain stage which is precancerous stage, you can treat it within 5 to 10 minutes, even in remote locations. But it is still one of the biggest killers in countries like Nepal. There are multiple reasons for that, lack of awareness, lack of screening, all this. But typically in the West, this has been reduced because with the pap smear test, what you call as pap smear test. But pap smear test needs sampling, just like swab. You might have seen in COVID, you do the swab from nasal. In cervical cancer, pap smear you do from the cervix. They need to take a swab. It has to go to the microscope, and the pathologist has to see, and then usually it takes a couple of days or 1 day to get back the results. But this kind of setting, it's not easy in remote settings in countries like Nepal, because women have to travel long distances just to coming, asking them to come back again just to take the report is hard. Getting pathologist is hard. So there's a lot of nuances. That's why it's not scaled. And this screening needs to be done every year, actually regularly, to all the people. So what what people do in these settings is visual inspection with cervical acetic acid. So this is a cervix here, and visually gynecologists usually see that, and if there's a precancerous stage with a reasonably good sensitivity and specificity, they can identify that. Or if it's suspicious cancer, they then refer to further biopsy and further test. But if it is just precancerous stage, they can identify fairly confidently. They can either ablate, which means burn the tissue, or freeze the tissue with the nitrogen gas, I think. So you can do that within 5 minutes. So thermoablation or freezing right there, so that the woman doesn't have to visit again. But the challenge, so we do not have gynecologists on all these places who can regularly screen. Women could go just to the health post all the time and just get access to this service. So what the governments around the world, especially in Africa, in South Asia, they do, they train nurses instead of gynecologists, because nurses are usually available in community settings, and they want them to detect this precancerous stage. But what we found when we talked with nurses, we went, visited, and saw what they were doing, is there is a challenge. The accuracy suddenly drops down with the nurses. It's because it's a very subjective way of testing. You need to visually see this region on the bottom right, and then they have to assess how much aceto-white. Once you put the acetic acid, it changes color, and the cloudy, certain kind of features, all these details they have to see. So it's subjective, and it's usually you need an expert, but then nurses are trying to do it, and it's not as good as the gynecologist. So this is a classic example of where AI could really help with AI-powered task safety, because now you could build, hopefully, an AI model that can see those images and then or assist these nurses to be able to more confidently and more accurately and more reliably predict precancerous stages. So this is the project we're doing. Still, when there is one first version out there, but we still need to, it's still the first step, and we're still doing that, where what we did was, and this kind of problems typically, when you have done many, I'm sure many of you have trained AI models, and most of the time what do? You get public data available on internet, you download the data, you download the model you train, and then you get 95 or whatever percent accuracy, and oh, we got this accuracy, we know AI. But real world, it doesn't work that way. So even for collecting data, because this is cervix and we want to use smartphones to take the picture from the cervix, so there's a lot of nuances, issues. How do you design it so that it's not so invasive or it's not so awkward for the women? Because so it has to be in a flow where it's typically already done. How do you make it as same as possible? You don't want to introduce completely new setups for the nurses to do that, because they are going in remote settings, in camps, organizing camps to do this kind of screening. And then we initially thought we would build a stand so that we get a very nice image with no motion, and then we put on top of a stand or a tripod, put a phone, and then acquire images. But they go in such a difficult, sometimes it's merely a bed is available and nothing else. It's not possible to put this stand. And then we try to take images, pictures, then again, it's difficult for the quality. We don't get quality. So all this protocol, even defining a right protocol for data collection, defining what kind of data you want to collect, all these things are important, and you need a deeper understanding, or you need to do research within that also. And it's part of AI system development. And this is one of the crucial parts usually that needs to be done. So we went through multiple iterations and designed a way to collect the data. That's data collection with the app where they have a phone, and then all these quality control metrics are there. Then it goes to the server, where then we need to annotate those. So that's another part where you need ground truth labels, training the model, and then we did this with roughly 1,600 or 1,500 women collected data. And so I'll not go into the details of all these PIA, pre-VIA, post-VIA, but I'll just quickly skim through this. You can look at the paper if you want, there's the link. And in the questions, I can come back if you want, but I'll just show this system in terms of this is the annotation tool. So all this data comes anonymous. So in healthcare, it's very important that you don't identify patients with whom you take the data, especially with people who are not allowed. Most of the people are not allowed to access the data, right? It's a private data, so it has to be anonymized. Once it's anonymized, then you start annotating those, and we built quality control mechanism within the annotation system so that we start getting better images, or we give quick feedback to people who are collecting data on having this lower quality or not useful data. And this helped a lot to identify important parts of how best to collect this data, because you want to have a clearer view of the cervix, not blurred, to be able to detect. And then the model, I think most of you know the standard process. Once you have the data, once you have annotation, it's the fairly simple part where you train a deep learning model and then you test on a test set. But originally you get the data like this, and then there's other pipeline. First you need to extract, you need to crop, all these things you could do with various deep learning models. I'll just go quickly through these. But it can be difficult. For example, I mean, it's not an easy problem. So it's highly subjective, and also the false, for example, when you look at the false positive or false negative pairs, it's not easy to distinguish which one is, at least for the normal eyes and gynecologists. So the goal is to be as good as gynecologists in the first place. That's one project that's ongoing. Let's look into another project. Once again, lack of experts, similar settings, AI-powered task shifting, what can we do? And ultrasound is something, once again, I think it will be really transforming healthcare in certain ways, because these days you can get ultrasound that is handheld ultrasound. That means you just have this handheld size, typically like smartphones. You get a probe for audio, because you can see here in the pictures, and then on the phone you can see the video. So that means because previously, maybe a decade ago, even until 5 years ago, not these handheld, or even now not handheld devices are not widely accessible. So it's portable ultrasound or bigger machines, which is not easy to send on all these remote places or emergency settings, even in big hospitals. But now with these low-cost devices, that is low-cost and handheld, you can send devices all around the world. And you can do many, many things with ultrasound, but still it's not solved. Do you know why? We can send the devices in low cost and then use it. But the problem is we need an expert to use the ultrasound. And this is again challenging, because it's usually a radiologist. And radiologists there's very few radiologists in most of the resource constrained settings, because they mostly are concentrated in the big hospitals. And without the radiologist, without being able to go to right places, you cannot really do much with ultrasound, because you need to take right images and then diagnose properly. So acquiring is already a challenge, because it has limited views, field of views. Here what you see is some parts of fetal brain. That's the images you are seeing here. So you can see specific slices, small portions of brain. You need to go to right areas with the experts, and this is a challenge. So even with low-cost device, unless you have experts, it's hard. So what can we do? Again, similar as earlier, can we train nurses or the local medical office, even midwives, or even female community health workers, right, to be able to just use the ultrasound and get results? And obstetric ultrasound, that's where we will focus, is many pregnant women. So if you look at the many low-income countries, the mortality rate, women dying during pregnancy is much higher in low-income countries compared to the high-income countries. And there are, again, multiple reasons, but one of the important parts is also being able to diagnose early or to identify the pregnancy situation. So there are various things you need to look into. and here it's 3. So in ultrasound imaging, you need to find right views, you need to detect, measure, and all in real time, usually, because we are doing it in real time. Here you see a fetal head, a fetal abdomen, and a femur. All right. So we will look into this into two contexts, one from machine learning perspective and one from, again, the low resource setting and task shifting perspective. You want to be able to go to right areas and detect. For example, here we're saying some congenital heart disease. If you want to look into heart disease, you want to be able to identify those structures. It's a fairly hard problem. You need a radiologist that is trained really a lot. For example, I mean, to give you the picture, if you want to understand fetal congenital heart disease, I did pick them early. Even in Nepal, and there's only one of our partners, collaborators, who's working with us. I think he's one of the first who is trying that in Nepal. And even in UK, where I was working, there's very few experts who can do congenital heart disease. And there's still some open problems. So these are difficult, but even for the simpler ones where people are doing it for years, basic anomaly detection, basic fetal presentation or the position of the fetus, those are also not accessible in many rural areas. And again, the point here is in ultrasound, you need to go and find right views. You need to detect something or measure something and then do diagnosis. So where does AI come into picture here? So you can think of automatic view classification. So you're going in a video, ultrasound video, different things come, and then as soon as the right view comes, you detect, oh, this is the right view. Or you take a video and then you find all those right views for their measurements. That's one thing you could do. Where usually the probe is handled by expert because they know where to go. Because if AI has to detect a right view, there has to be a right view first. And without experts, it's usually difficult to have the right view sometimes. Maybe there's the other ways we're exploring, we'll see later, but usually you need an expert to at least have the right view. The other direction AI could be helpful is to guide non-expert to go and get the right views. Right? And the third one, which looks promising, which is what we are exploring right now, is also what we call as blind sweep. What it means, we will see later, is it's non-expert, but they don't really care about where they are going. But they try to get as much as possible, everything. And then let the AI find all the right things there. So it's a simpler problem to at least acquire images, but harder problem for AI to really get things that is needed. Now, if you look into the ultrasound literature, most of the AI and ultrasound, most common and most model propose, most of the work in AI that is done around the globe had been on these identifying right views or measuring something from the videos that was acquired by experts. But in our settings, we want to enable non-experts to use ultrasound. So this is not so useful for us, at least for that direction. Because by design, we want AI models to get images or videos that is being captured by non-experts, or at least those videos that is similar to those non-experts. So most commonly done research that's still useful, but not the direction we want to go. Second, guidance to non-experts. There are some interesting directions people are working on, but many of these are still unsolved. Very exciting, interesting open problems to work on, and we are working on those as well. And the third one, which looks interesting and it's recent, but quite a few groups now in the world are trying to do that, and companies as well, is blind switch. So let non-expert take as simple as possible videos, and then the AI does the rest. So on those directions, we had been working for a few years. I'll go quickly with this because I think I have now just 30 minutes. But for example, if you want to measure circumference, head circumference of a fetus, typically you can have a training data, you train unit-like architectures. I'm sure you've seen unit, those kind of architectures, and then you get results. But if you want to do uncertainty, because you're in a confidence, and then you have other things you need to do, the other direction I had been exploring, and I'm still exploring, is how do we do everything together? Just like a radiologist can go around everywhere. They think, and then they move their probes just like here. But then they always have something, there's a constant feedback of what they see and where they want to go, and then they navigate around to go to right places, and then measure and then diagnose. So can we do this whole navigation with an AI? So what are the steps? There are multiple steps involved. You need to know roughly where you are, then you need to know in detail exactly where you are, you need to know what images are right or not, you need to do images. So there's lots of things happening, and it's a very interesting problem, an open problem. But I really believe with the way the deep learning models are going and the amount of data we will have, this is something achievable in the near future. But you tackle those at different scales and different ways. Here, okay, if it is very hard to identify the exact plane, exact small area, can we roughly identify where we are in terms of, is it abdomen, is it heart region, or is it head, limbs? Because that will solve first step, and then you could go to the another scale. So this kind of work, and because in a longer research you do stepwise multiple things in different directions, right? Or if you have a video or a 3D image, can you get the right plane within that? That's another settings where we could work, and this is the other works we were exploring, where you have a 3D volume, multiple slices, and you want to identify the right slice within those volume. This could help perhaps if a non-expert is going around roughly without finding exact plane, and then you try to guide them with the right plane. Or you just let them go around without any specific guidance and just combine all those images together to get 3D. So this is what we're doing here. On the right, on the top, the nice smooth figure is from the AI model. The bottom is the expert sonographer in London trying to do that for difficult cases. And this is for the difficult cases for humans. When it's easier, they usually do a good job. But without guidance and without experts, which is the typical settings we want to work, what can we do? So this is the blind sweep protocol that we are exploring. You can do 6, 8, 5, again, people trying on different ways, and we will see which ones is really, which will be most useful. But there are multiple hypotheses and multiple explorations going on, where you define how you want to take the ultrasound images and then do the rest. So there's some promising results where they show for gestational age estimation of fetus. So for the baby inside the mother's abdomen or womb, what's the age? That's an important marker or an important number that is needed for pregnancy management. And with just a blind sweep and AI, it seems it does fairly well, as good as radiologists. So that's interesting. And then we're trying to explore new topics. So there's one project going on with the teaching hospital together, where we are trying to build AI models for multiple important biomarkers or markers that are ultrasound markers that are important in obstetric ultrasound. We are also working with GE Healthcare. Killian is here. I think he will give a talk tomorrow. Yeah, so we are also working with them on estimating quality for this kind of blind sweeps. Lack of device, let's go into another. So now lack of expert, I hope you understood the context from 2 examples, but there are many others that needs to be done. But devices or algorithms, or when it's expensive, let's say. So for example, CT scans. So most of the CT scans are not available, or microscopy is not available. So here we'll see microscopy, where with a collaborator from Kathmandu Institute of Applied Science, what we have is a low-cost microscope, which is on the top. You see basically your smartphone with a very tiny lens. You can convert it into a microscope, and with that you could then, for example, do a 3D printing. You see on the images there also. So we can make a very, very low-cost smartphone as a microscope to look into tiny objects up to a certain scale. Not everything is not, so usually the parasites. So what we are targeting now is the diarrhea parasites. Diarrhea is still a major problem in countries like Nepal, and for children especially. Sometimes you hear in news, 10 people died, 10 children died of unknown disease, 10 people got, 100 people got sick from unknown disease. It's usually most typically diarrhea related parasites causing that. And so on the top you see traditional microscope, the standard microscope used. On the bottom row, you see smartphone microscope. But the challenge now is it's more noisy, it's slightly more difficult to see things. And even if you make a smartphone microscope and send it everywhere in all the areas, you don't have pathologists you can detect. And that's where AI comes in here also, and to build models that can detect. And this can be useful for water, vegetable, even in preventative settings. So that's why we built recently a large data set of a few 100,000 images from four different provinces for water, vegetables, and stools. So it can be used both for preventative and also for diagnostics. With stools, it's for diagnostic purposes to identify parasites. And with vegetables and water, it's for preventative. For example, we had a big flooding in Nepal recently, right? And then what happens? After flooding, water systems get contaminated. So if you want to check quickly on all these places how things are, again, with the traditional microscope, it just takes long. But you could think of this low-cost, smartphone-based microscope that could be quickly used anywhere, and then you test. So this is also interesting. Another example I think I gave in the opening ceremony from the doctor, one of our co-founders who works and goes to remote villages to do surgery. They don't have CT scan. And just with X-rays, you cannot see the whole picture in 3D. But can you build 3D reconstructions from X-rays? So that's something we are working on, and I'm not going into details. This is in the New Rips paper that you can find and read in detail, or in Q&A I could go into detail. But what is the limitation, the way things is being done right now? There are certain limitations on validation, evaluating, and analysis, and what we built was a 2D to 3D benchmark. I'll skip these, we can go later if you want, and why clinically very relevant metrics are important. So most people work with dice scores. We might have done segmentations and dice scores, but then for the surgeon, dice score does not mean anything. What they want is the clinical decision making or surgical planning, and for them clinical parameters are important. So we were looking into deep models on how they estimate on the clinical parameters, and these details on domain shifts, because most of the work were with the normal population or normal images, but this is mostly useful for abnormal cases. So we need to see what happens in abnormal. If there's a fracture, they want to do a surgery, that's where we need to know how accurate these are. So those kind of details we worked on to show where there is biggest problems. Some examples on why dice score is always not a good score. You could have a better dice score but a worse clinical parameter estimation. So these scenarios, we showed it from multiple ways. Okay. Now, let's go to another one in terms of lack of data or internet, so compute resources. So I'll go quickly with these. I mean, there's lots of technical details. In 1 hour, it's hard to explain everything, but in low resource data, if there's low resource data, there's different things we could do. Weekly supervised, I showed one ultrasound earlier, means you do very quick weekly supervision means you still give supervisory signal, but this is not as time consuming as you would need usually. For example, in segmentation, if you want to do a segmentation, you need to delineate the whole structure. In 3D, it can take a lot of time. But what if you can give few dots or a box instead of detail, and then be able to do that? So weak supervision. Semi-supervised means you have small amount of labeled data, but huge number of unlabeled data. And how do you leverage those unlabeled data? So that's, or unsupervised, there's no labeled data in those scenarios. There's few work we've been doing. Synthetic data, if you don't have labeled data, can we generate synthetic data and use it? So on this, when there's low resource of data, so there's multiple directions you can take, and few of our papers where we've worked in the last few years. Or low resource compute. You have less computing resource either during training or during deployment. What do you do? So there's different directions: parameter efficient fine tuning, or not even fine tuning at all, using adapters, prompt tuning, or doing fine tuning with adapters and lightweight blocks. So there's multiple directions we are taking. Some of our recent papers you could look into if you want to get into details are there. So the third kind of lack of expertise I said was the low resource was lack of research and innovation. And we are, for example, tuberculosis is important. So Raunak is an faculty, and we're working together on trying to detect drug resistance in tuberculosis, and also to understand better how the different mutations work, or if there's any specific interactions of different mutations on drug resistance. Maybe this is a good time to also let you guys know, if you are interested, there's a very good research opportunity. There's a vacancy ongoing where I and Raunak, we will be supervising this project on tuberculosis related to RAs we will hire. And the good thing is you work with us for 2 years as a RA paid. We, of course, there will be a salary, but you will also get a master's degree in those 2 years from Kathmandu University as MS5 research. I think this is a really good opportunity, so I hope you guys will apply. Thank you. Emerging technologies, as I mentioned about ChatGPT, and we're trying to evaluate this in sexual, maternal, reproductive health settings on what are the key gaps and risks of using ChatGPT or those kind of large language models as of now. So that's the first step we did, and there's a paper in submission right now, and then we will look into how to build better models. Trustworthy AI, I will go very briefly on. In AI in healthcare is especially even more important because the risks are very high, regulatory frameworks are there, and we need to really look into it from health systems perspective also. Again, not much time to go into detail, but I would encourage all of you to read this paper. We just got published actually in BMJ, which is one of the really good journals in medicine, where we try to frame the whole trustworthy AI in principles, 6 key principles here: fairness, universality, traceability, usability, robustness, and explainability. So you have to look into the paper to get the details. It's future AI, and there are more than 125 scientists from around the world. We are involved to build a guideline on how healthcare or AI should be deployed, how it can be made trustworthy in AI. So this is something interesting. And finally, another research direction I'm really interested in and we're doing right now is on, again, some sense trustworthy aspects, but how do you both use images and languages? So language as prompts or inputs in the clinical thought process or radiologist thought process when they are interacting with images and AI model. And so these are vision language models. So we recently had a paper in middle. Again, very useful paper to go through. And I would conclude here, and I'm open for questions. Thank you.
My name is Himanshu, and my question, in the context of tax score, you said it's not a good metric. So could you explain why it's not a good metric, and some other evaluation metrics that could be its alternative?
So, DICE metric is not a good metric itself, is not a complete sentence. What I meant was in certain contexts. So it depends what context and where you're using. So DICE scores are very good metrics for certain scenarios, especially in segmentation. If you just want to look at the segmentation scores for different sizes, it's fairly good metric in some sense, right? But for example, here, if you want to do 3D reconstruction, here it's a vertebra. So vertebra is one of the on the spine, right? And as you can see here, for the surgeons, if they want to do a certain surgery where they might have to get inside that this space you can see inside in the middle, they have to go through those space and then do certain manipulation. If they want to plan those, they need to know angles, like here the NSA, or there's certain specific structures they need to know. And you can see here, for example, you have a DICE score of higher DICE score but more error in the angle. So in these scenarios, DICE, so if you want to, for this specific context, DICE score is not a better metric. right? And you can give many, so we give three examples here, but you can give it to many other examples. So it's what I meant was, for this specific case of doing 3D reconstruction and using it in surgery, the I-score may not, or actually is not a good metric for that context.
My name is Pawan Kumar, and I am from Singapore, Batika Sultan. Why I mention my address? Because there is a sometimes we usually call peon, but peon of the healthcare works the role of I have a army, and they faces sometimes faces like legal challenges. So they are integrating AI in the healthcare. What is the context of Nepal using AI in the healthcare from the perspective of legal angle?
From the perspective of
legal angle. From legally, how AI is can be how AI can be integrated in the healthcare. What are the processes of legal process? I mentioned that sometimes even people do the work of AI and faces challenges legally.
Yeah, that's a good question and not easy to answer because there's limited regulations or policies on how AI should be deployed. Even globally, there's lots of developments happening, and for Nepal, it's even more difficult. But as of now, I think it's been there needs to be obviously a validation and some regulatory bodies approving these things. But as a technology, if it's good enough, it can be used. And the other important part is how do you evaluate or validate a model, and its accuracy should depend on context, exactly like you give. So, for example, let's say in a screening context, a model has 60% accuracy, or it can pick up 60% of cases, let's say. And this might not be good in a hospital setting where the radiologist usually is available and they can pick, let's say, 80% of cases, for example. But should we use it or not in settings where there is no one and there is 0% opportunity to pick up these cases? So 0 versus 60, right? So whether it's good or bad also depends on the context, whether it's improving the existing scenario or not. I think that is also important, and also from harm perspective, whether it's harmful or not, we have to look. And from legal perspective, these are, I think it's a work in progress. Governments or ministries, they should start looking into how to build legal, but it's always the case, right? Technology is always ahead rather than legal, and we need to catch up.
Hello, sir. So all of the vision topics and the work you have done is really commendable. My particular question is, you addressed the topic that going to the community and taking the samples for the cervix that one project. It is invasive, and what are the proposed solutions that you are trying so that it becomes less invasive, and how are the people from community acting when the process might have been a bit different, right? When the nurses took the smartphone and took the samples. So what was the community's response, and how are you planning to make it less invasive?
So the visual inspection with acetic acid, even without AI or without smartphone, it is usually done. And even doing that, you need to insert a speculum, and then it's already there, and it's usually, except for people do that. So what we're doing is we're just adding the phone, and which is usually, if you do colposcopy, which is another typically done practice, there you need a camera already. So it's not something new we are doing actually. It's something that is already embedded. Yes, we were concerned in the beginning, we need to use the picture, would they be comfortable? But I think there were no single woman out of 1,000, more than 1,000, because we take consent, we ask them, and then no one was bothered with that. Because it's not different, that it's not like whole picture, it's really, because once it's almost looks like a procedure, it goes really on what the nurse is doing, right? For that particular case. But then what we are doing in terms of non-invasive, that's a bit out of scope for us. It's more from the research direction. I think people, yeah. Or what others are, I'm not doing anything, but people are doing, for example, vaccination, which is promising. And for young women, I think that's the best thing to do. And the government of Nepal, I think just a few weeks ago, they announced that there will be vaccinations for, I forgot the age, but I think it's from 8 years to certain age of the young adolescent girls. You can take the vaccine, and that's the thing to do. But for people who are adult, I think all the women, they have, till now, yeah, we don't have non-invasive options, so it's pap smear, or there's there's something with not gene expert which is tuberculosis, but something with the genomics or the PCR kind of thing that one could do test for the virus, because it's usually human papilloma virus, HPV virus, that causes then later the cancer. So detecting this through the PCR kind of technology, or pap smear, which is usually in Kathmandu, I think pap smear is the easiest thing, and it has to be done regularly as once you are an adult in a risk group. For the screening, those are the options for now for older adults. Yeah.
Good morning, sir. I am Rekha Public. And my question is, since AI applications are detection and measure masani already भइसकेको detection का accuracy चाहिँ कति छ? One question. अनि अर्को चाहिँ यसको काम later on diagnosis मा पनि utilize हुन्छ or not? जस्तै त्यो precancerous cells हरु identify गर्यो, पछि त्यसले burn गर्न सक्छ कि सक्दैन AI application ले?
Okay. So the second question, I think, is once it detects the precancerous stage of cells, can it burn with the AI? So that's more treatment. Can it treat? So yes, in surgical treatment. So usually AI or medical, you can use it. The people working on diagnosis, prognosis, which means how the disease goes or progresses. That's prognosis, and therapy planning, which can be either surgical interventional therapy, or it could be with the drugs that medicines that one gives. So in all this spectrum, one can use AI in different settings. For the second question, so for burning especially, it's easy just with this. But if you want to be really precise, or if you want to do the tumor resection, where you need to cut a tumor in a cancer on this, if you want to be really precise, yeah, AI can help you guide to that. So that's more therapy planning. The first question was, what was the first question? Yeah, accuracy. So there are many detection algorithms and quantifying algorithms. What's the accuracy? So it depends case by case. But for example, the gestational age estimation, the paper that was published recently, the one I showed, that's not my work, but the people who worked, I think there's a large group of people who worked on that, and it's better than radiologist, for example. And there are papers which they show, for example, in tuberculosis, for triaging case from chest x-rays to detect AI. This is something that people have done, and there's companies who are selling these products across the world, and the World Health Organization has put it in the official recommendation on one of the ways to triage or detect the tuberculosis. And this comes after sufficiently good accuracy in that context, right? So it doesn't sense to put a number 80, 90 or 100 because it's all contextual. But yes, there are many detection algorithms or quantitative measures that are good enough and being used in clinical practice right now.